Welcome back to another episode of Stat 479 Time Series Analysis. Today we'll be moving into a new section on smoothing for time series. So let's go take a look at what that's all about. So data can be quite noisy and quite bumpy. And when we look at time series, we see a lot of noise. It's often really nice when exploring time series data to try to reduce the noise, and by doing that, we're going to use smoothing methods. So today's lecture is very self-contained. What we'll be doing is looking at a variety of different smoothing methods for time series that we can then apply to get a sense of the trend, our overall patterns in our data by kind of getting rid of some of that noise. So let's smooth out some time series and see how that looks.
And we're back with another lecture of Stat 479 Time Series Analysis. Today is a really self-contained lecture. We're going to talk about smoothing methods for time series, and this is a very useful tool for exploratory data analysis when we're looking at time series. The idea is that time series are very noisy, right? We've already looked at some examples of them, both simulated and real data. And what we find is that while there's a lot of noise, it's not always clear what's going on, what are the trends, what's happening. So smoothing methods, what we'll be talking about today, take the idea of trying to, smooth out the noise to make it a little bit easier to see what's going on in our time series. These types of tools show up a lot in data visualization. We see them in, the news all the times, where we have some noisy data, whether it's stock prices or COVID cases. And what they do is they smooth over them to kind of show you an overall average or trend as to what's happening with the time series data. So with that, we're going to talk about a few methods today of smoothing. And again, it's somewhat of a self-contained lecture. It's not going to directly apply to the topics that we'll be talking about going forward from here. But it's still very useful tools to use and something you might have to use yourself when you're working with real data. So let's get into the notes. All right, so today's lecture is going to be about, smoothing, as I mentioned. And we're going to discuss a few different tools that you can use when you want to smooth data. And the idea is really just to give you some tools for your toolbox so that you'll know what they are also if people are talking about them in the future. So the first is actually something that we already saw. It's the moving average smoother. So the first thing is going to be our moving average smoother. And this is simply what we did before when we generated our own moving average process. But just to be explicit, we'll write it out again. So the moving average smoother, MT, here I'm going to use MT to be the smoothed process. So actually, just to be precise, what I should say up above is that we'll say something like let xt, let's say t from 1 to capital T, be a time series, whatever that means, right? So we have our time series data for some fixed amount of time. And what we're going to do is we're going to try to, smooth it out. So MT is going to be our smoothed process. And the moving average smoother is simply something that we looked at before when we applied it to the white noise process. And that's that we choose some R. R is going to be kind of like the bandwidth we have here. And we're going to take J, our index, from minus R to plus R, and we're going to sum theta J X T minus J. Again, time series is kind of quirky, and we typically index X backwards, which is why it's minus J. For whatever reason, that's typically the way that it's done. Okay, so what are we doing? Well, what we're doing is we need to basically choose some thetas, theta J's. So for example, what we can do is we could just choose that theta j is equal to 1 over 2r plus 1. 2r plus 1 is the number of terms in the sum, right? So we're just basically averaging now across some window of width 2r, I guess, plus 1 for the center point. So this would be a, this is just an average. So that's one way to do it, but you can also define other thetas. You can have them kind of taper a bit. You could have them taper down. You could choose different values of theta to determine how to average locally the time series values. So this is, for example, when they say something like 7-day moving average. And intuitively, that's something that is useful because, again, if we're looking at, for example, COVID cases, a 7-day moving average will just tell us, well, okay, across a 7-day window, what's the the average number of cases per day, right? And this will give us some idea of the overall trend and kind of averaging out some of the noise. One day might be a little bit higher, one day might be a little bit lower. If we average over 7 days, we get maybe a cleaner picture of what's happening. And again, as we saw in previous lectures, this is implemented in R in the filter command. And later in this lecture, we will apply some of these methods to some real data, so you'll get to see how they actually work. But yeah, this one we've already looked at. It's not the most exciting, but it is good to write it down in this context because the next ones are going to kind of build from this one. Specifically, the idea of kernel smoothing. So let's write that down. Maybe we have our moving average smoother. And then we have our kernel smoother. So kernel methods are very popular in statistics. You can use them for smoothing. You can use them for density estimation. You can use them for regression. There's kernel regression methods. There's a lot of neat places where kernels show up. In this case, we're going to do kernel smoothing. So what we have to first figure out is, well, what's a kernel, right? So first, what we'll do is define a kernel. I'm going to use my little kappa here because I don't want to use k, because k is the auto covariance in this course. So we'll just use kappa h to indicate a kernel with bandwidth h, a kernel function that is with x and x naught. Okay, so what is this? Well, this is a we'll say non-negative function, which is, that is, I think decreasing. You could probably have non-increasing, but we'll just say decreasing in x minus x naught. So x naught here is going to be the center of the kernel. So I'll put that here. X naught is the sort of the center of the kernel. And h is the bandwidth. So the idea being of how concentrated the kernel is or how spread out it is. And then there's lots of different types of kernel functions that we can consider, and ones that are quite popular. Oh yeah, there's also one other requirement, which I'll say also, we need this to be integrable, or yeah, integrable. So what we need is, we need that if we integrate this thing, let's say from minus infinity to plus infinity, kappa h x naught dx, well, we need this thing to be finite. Yeah, otherwise you can have some weird things. So basically don't use like the Cauchy distribution or something for your kernel. It's not going to be a good choice. Otherwise, most things you would think to use as a kernel function will probably be fine. Right, so then we need some examples of what a kernel function is. So there are some popular ones. There's the Gaussian kernel, which is, well, probably what you'd imagine. It's a little bell curve, right? It's basically the normal distribution without all those normalizing coefficients out front, because who really cares about those? Right? What it's going to be is it's going to be something that looks a little bit like this. It's going to be the exponential function, exp, of minus x naught squared. I guess I don't strictly need the absolute value, but that's okay. Divided by 2h squared, where h again is the bandwidth. So in this case, right, what we end up with, I'll draw a little picture here, is going to be, well, a little bell curve. It goes on forever, right, in either direction, but it decays to 0 pretty quickly. The center of it is going to be x naught, and roughly the right, h is going to kind of correspond to the bandwidth, or it's kind of like the standard deviation in this case. If you were to think about this as a normal distribution, but in other cases it will actually, but you know, the normal distribution keeps going on and on. But the smaller h is, the more sharp our normal or peaked our normal distribution or our Gaussian kernel is. The bigger h is, the more spread out it is over the time span. Right, so we have that one. We also have the triangular kernel. You can take a guess as to what this one looks like. Right, the triangular kernel is going to be, well, something that looks like mathematically 1 minus our x naught divided by h plus. So this little plus sign, and I'll define it in a second, means just take the positive part. It's a shorthand, so we'll say a little side note on notation. And the notation is that, I don't know, we'll say, I'll just use what I wrote there. Let's say x, what's the best way to write this? We'll just use maybe a y, just as something else. So if I say y with in parentheses with a little plus there, then what that's going to be is it's going to be y if y is greater than 0, and 0 if y is, well, I guess less than or equal to 0. So the idea of the plus is just a shorthand to say that if it's whatever's inside there, if it's negative, just set it to 0. Otherwise, keep it as it is. So what we end up with is this triangular kernel, and the triangular kernel is, well, going to look like a triangle. It's going to be something like up and down, and it's going to stop, right? It's not like the bell curve or the Gaussian where it kind of slowly spreads out off to infinity. In this case, it actually stops as soon as, I guess, the difference between x naught and x is h. So I should say that these axes, the horizontal axis, both for my Gaussian kernel and my triangular kernel, are going to be x, the variable, and x naught is a fixed point. That's the center of the kernel. And here, the distance between, well, I guess x naught and where my triangle hits 0 is going to be a distance of h. So the, I don't know, width, the length of the base of this triangle is going to be 2h, if that makes sense. Right, so we'll have one more example, and there are a few more, I think, implemented in R, and you can go check them out yourself. But another one that's very popular, especially in things like density estimation and kernel regression, is the Epinechnikov kernel, if I'm getting that close enough. Epinechnikov. Try to get that to spell it, try to spell that correctly. The Epinechnikov kernel. And this one is basically like the triangular one, but it's it's quadratic. It's an upside down parabola. What it looks like, well, mathematically, is going to be something a little bit like this. So what we're going to do is it's going to look a lot like the triangle one above, except that now I'm going to take my x minus x naught, and I am going to square it and divide by h squared. And I'm still going to put a little plus sign here with the parentheses. So again, in fact, I'll just squeeze that one in up above because it should be pretty straightforward that the triangular one is the first one. And then my Epinechnikov kernel is going to look like, well, a little upside down parabola, something like this. And again, x naught is going to be the center point. The width or something, or the length of the base, is going to be 2h, so h there from the center to the end. And this is going to be indexed in x here as our argument. Okay, so these are just different kernels you can use. They have some nice properties. For example, if you use a triangular kernel, well, then what you're going to get is something piecewise linear. If you use the Epinechnikov or like quadratic kernel, you're going to get piecewise quadratic. If you use the Gaussian, then you'll have something that is sort of smooth throughout. That is, has all the derivatives you'd ever want it to have. Okay, so then the question is, well, how do we actually use these kernels in time series, right? Because I spent the last 6 or 7 minutes just explaining that we have different types of kernels we can use. How do we actually use them? So now I'll say a kernel smoother is, in this case, I'm going to say finite time case. What it's going to be is it's going to be a, I'll say in this finite time case is a, I'll say MA for moving average smoother with theta, right, our argument from above. So it's the same moving average smoother I had above, though now that I think about it, I should put a J in here just to try to coincide with what I had before in the notes. And what we're going to do, yes, and what we're going to have here is we're going to have K H at J and 0 and K H, oh, this is the sum of them all, sorry, I forgot, I need a summation here. We're normalizing it so the thetas all sum to 1 when you sum them all up. That's all that we're doing with the denominator. I probably shouldn't reuse J. We'll use I here just to keep it somewhat. Now I've switched it from my note, so if you're reading along, apologies for that. Something like this. So what we're doing is we're taking this kernel and we're discretizing it, in this case over R, I guess over a window of length R. So we could take R, say, to infinity if we were doing the Gaussian kernel. Of course, well, mathematically, it would still be the thetas would be non-zero, but in practice, they would be so negligible that it wouldn't really matter. But to try to explain what this formula is actually doing, right, what we're doing is we're, say, taking our, let's say, our triangle. Well, it's centered at 0, so here's what we'll do. What we'll do is we'll take this triangular kernel like that, and then using it as a kernel for smoothing a discrete time series like this, what we end up with is actually a bunch of discrete point values, something like this, which are going to be the thetas, maybe that. And similarly on the left-hand side. if I got the same number. All right, close enough. So the idea, right, is that this would be let's put it in red. Over here, we have the kernel. And over here, we have the thetas. If I can spell that correctly. Thetas, there we go. So this would be like theta 0, theta 1, theta minus 1, etc. Yeah, so and then we would just normalize the thetas so that they sum up to 0. And then the idea is that those would be the coefficients for our moving average smoother. So in some sense, yeah, this is just the moving average smoother with a more clever way of how to choose theta than just setting them all to be the same value. And it does have a way of emphasizing, say, if we had if we used a kernel smoother like this triangular one, it would be still averaging over, say, a certain number of days of our time series, but it would be putting more emphasis on the current day and the adjacent days and less emphasis on those further away, compared to the example I did above, the 7-day moving average, which would just equally weight all 7 days in the window. So again, these are different ways that we can apply smoothers. And this one is also in R as the function k smooth. Should be a lowercase k, but yeah, it doesn't really matter. So you can apply this very quickly to a time series in R, and we'll do that in the second half of this lecture. All right, there's a third method that I want to talk about very briefly, and that is called the LOESS. I'm going to write it in caps because it's actually an acronym. It's somewhat of an acronym. The LOESS smoother, which is the locally weighted scatter plot smoother. And this one is actually quite effective. It also exists in R as the function just LOESS there. And yeah, I kind of challenge you, try to figure out exactly what this thing is doing. You cannot find good documentation on this anywhere. It's quite annoying because it's actually quite an interesting method and it's quite useful. I'm not going to get into all of this. If you actually read the manual page, you will see that it says it is defined by a complex algorithm. Ooh, very mysterious, right? Effectively, just to give qualitatively what's going on here. So we'll say roughly, it takes a window, much like all of these methods do. It takes a window, let's say xt minus r through xt through xt plus r, and fits a low degree polynomial regression. But there's a lot of other stuff going on with weights and other things that are not really well written out anywhere in either the documentation or other places. So maybe there's a good source for figuring out exactly what this is without actually reading the R source code, which is probably a terrible idea. Otherwise, it doesn't really matter, again, the specific details of this method. I just found it quite peculiar when I was first working through my notes and realizing that I cannot find a good, easy way to easy explanation of what this code is actually doing in R. So yeah, we'll leave it to the mysteries of R. But there is another method that is much easier to interpret, and also is one of the most popular methods, and that's the cubic smoothing spline. And we'll be talking about that just in 1 second when I have a chance to reset things here. And we're back, and we're going to be talking about one more method of smoothing before we move on to our R demonstration. And this is going to be the cubic smoothing spline. Cubic smoothing spline. All right, so this is actually quite a popular method. You can do smoothing splines of different orders, quadratic or higher, but cubic is kind of everyone's favorite in some sense, because it gives you just enough derivatives to make things nice, but not too many to make things, I guess, too over-structured or tricky. Anyway, first, before we talk about a cubic smoothing spline, we have to talk about just a cubic spline. So first, we're just going to talk about what's a cubic spline. Well, this is effectively like doing linear regression with a cubic, but in a local sense. So what I mean by that is we first we partition the time. Well, first we partition time, we'll just say. So that's kind of a cryptic sentence. What I mean by that is that, say time into, let's say, k intervals. And what I mean by that is that we're going to start with our time. Remember, we're going to run our time from 1 to capital T, whatever that is. So we're going to set little t sub 1, our first sort of not point is what they're going to be called, is going to be just the point 1. Then we're going to select some t2, some t3, all the way up to, some t, and I'm going to say k plus 1, and that's going to be capital T. So effectively what I just did was I took my interval here from 1 to capital T, and I split it into some pieces like this. All right, so these are all going to be the various not points. If this is T1, then this could be T2 and T3, etc., all the way up to Tk plus 1. It's k plus 1 because that means I have exactly k intervals. So the point here is that I have k intervals and k plus 1 points, which are referred to as knots. And this is, I'll write that in, k plus 1 knot points. That's k, N-O-T, not. Anyway, right, so then what do we do if we want to do just a, where's my, there we go. If we just want to do a cubic spline, then what we're going to do is we're going to fit a cubic polynomial within each of these intervals. So basically what we can do is we fit a cubic spline, or a cubic polynomial, I should just say, polynomial in each interval. Something that's going to look like MT, my smoothed process. Here I'm going to put a superscript I to indicate that I'm in the ith interval. And what we have here is a bunch of coefficients like we would in linear regression. We have beta I naught plus something like, let's say, beta I 1t. Well, actually, why do the ... I'll just write the missing term. Beta I 2t squared and beta I 3t cubed. So this is effectively what we're trying to do, is fit some type of cubic in time, cubic polynomial in time in the ith interval. And I will point out things like we can, man, my colors are just not working. There we go. All right, and the idea is that we can impose that they line up at the knot points. So, right, if I just fit a cubic into each of these intervals, well, I might have one here and one there. But what you can also do is you can impose that they have to actually meet each other at the knot point so that we have a continuous curve, or possibly a differentiable. That is, it might meet in a smooth way, not at a joint, at like a kink, but at like a nice smooth meeting, which allows you to actually take a derivative then across the knot points, which is something that's nice. Cubic splines and higher dimensions and things are actually quite popular. They even show up in things like computer graphics, a lot of engineering. I think it's computer aided design, CAD, I believe is the acronym, where you use things like cubic splines to understand the surface or the structure that you're trying to model. Or if you want to be a gamer, right, and you want really cool graphics, you probably don't want a bunch of polygons. But so instead, you can use things like splines to interpolate the polygon points in say, a computer game. Right. Well, what we can do, and I'll just say, so thinking, I'll say as in linear regression, we can have F be our design matrix, which is going to give us something that, well, I guess looks something like that. Well, what are we going to have here? We're going to have something like, well, effectively what we're going to do is we're going to have our M hat, our smoothed process, look something like F, our design matrix, times the estimated coefficients beta hat. And if you remember back to regression class, we could just use our least squares estimator. And we have something that's going to look like F hat, F transpose F, inverse F transpose X. So effectively what we're doing is we're taking our cubic splines. The cubic splines are going to define the design matrix F. And then we apply this matrix F, or I should say this, well, what they sometimes refer to as the hat matrix, but it's, in this case, F transpose F inverse F transpose. And we take that thing, we apply it to our time series X, and we get out our smoothed M. So this is, right, this is the time series. And then this is kind of like the smoothing matrix. And this is the M hat would be the smoothed series. So that's roughly what we have going on here. But again, this is just cubic spline. So there's nothing really that profound here. We're just fitting a cubic polynomial. We could fit really any kind of polynomial we choose to our time series. But now it gets a little bit more fun when we do the cubic smoothing spline. So when we do the cubic smoothing spline, we're going to do the same thing we did before, but with a slight little twist. So I'll say the least squares estimator, which is just M hat, is the minimizer of the, well, yeah, I guess we'll just sum it. It's the minimizer of the squared error, right? It's the least squares estimator. So it literally is the estimator that is going to minimize the sum of the squared error. So if I take my m hat t and I subtract xt and I square it, like basically we're just trying to minimize that thing, right? We're trying to minimize the squared error. Right, but what we could do is modify that a little bit. But we could instead try to minimize a slightly different expression. And in this case, we're going to be taking t from 1 to capital T. We're still going to be minimizing the squared error, but we're going to add on what they call a penalty term. This, again, if you remember from linear regression class, is going to look a lot like ridge regression. What we end up with here is plus lambda, the integral of m double prime. I think I have s here, yeah, because we're integrating over the entire thing, squared ds. So now what we have is we have the squared error and we have a penalty term. So what the penalty term is going to do is it's going to smooth out our cubic spline or our cubic polynomials. So without the penalty term, we just have a cubic polynomial. The penalty term is going to enforce smoothness, and it's doing that by penalizing based on, remember, not m, but it's penalizing based on the second derivative of m. So, right, what's the second derivative? That's how fast it curves, right? If we have a cubic that has a very sharp turnaround, that's going to have a very large second derivative. If we have a very slowly varying cubic, it's going to have a small second derivative. So what that penalty term is saying is don't let the cubic oscillate too quickly. Don't let it make sharp turns, hence smooth it out. And that's the idea intuitively of what's going on here. So what I'll do is, well, all right, we'll do a little side note on ridge regression. But first, what I'll just say is that if lambda is equal to 0, then we have just least squares regression, which is just going to fit the cubic in the sense that it minimizes the squared error. If we take lambda to infinity, then we have, well, okay, what do we have? Right, what we have is if we take lambda to infinity, then what we're saying is we want you to fit something, but we can't have a positive second or a non-zero second derivative. The second derivative has to be 0, or else that lambda is just going to blow up the penalty term. So what we're saying is the second derivative has to be 0. And what are the only functions where the second derivative is 0? It's a straight line, right? There's no curvature whatsoever. So in this case, then we have a straight line. And that's about as smooth as you can possibly make it, right? You can't get any smoother than a straight line. So what I want to do, what we'll do is I will do a quick review of ridge regression. We'll talk about how the cubic spline fits into that, and then I'm going to just shut this down and we'll do some R code and you can see what it looks like. So what we'll say is, a side note on ridge regression. So, right, ridge regression, well, we have our usual linear model, say y is equal to x beta plus epsilon. And with, we got some banging up there, with least squares estimator. estimator just being beta hat equal to X transpose X inverse X transpose Y. Okay. But again, the idea of ridge regression is a shrinkage estimator. What it's saying is that we can add a little bit of bias to the estimate of beta in order to reduce the variance. It's this idea of a bias variance trade-off that shows up so often in statistics. And yeah, and I should say, first of all, where the idea is that beta hat here is going to minimize the squared error. So if I sum over, let's say, yi minus x, well, we'll just say xi beta hat squared, I'll say is minimized. Now the ridge regression estimator, minimizes what? Well, it minimizes, again, similar to what I wrote above, the sum of the squared error. I think I should probably write X transpose to be really pedantic about it, but we'll just leave it like this for now. Right, so what we have here is we have the squared error, but we're going to add on a penalty term, which is going to be the sum of the beta hats. We'll say J. So, and squared, of course. So what we're saying is we still want to minimize the squared error, but we don't want beta to be too large. And what we end up with is a closed form estimator. And the result, right, is we'll call it beta hat ridge, we'll just call it beta hat ridge. And in this case, what we end up with is X transpose X plus lambda I inverse X transpose Y. So again, I'm not going through all the details of why that's true. I know that I did that when I taught the regression class here. So if you took that with me, you probably saw this already. And if hopefully they're still doing ridge regression, because it's kind of a neat topic. I mean, I really like it personally. But regardless, yeah, that's roughly what, there we are. That's roughly what's happening with ridge regression. The idea is we add on this penalty term, and then it modifies the least squares estimator a little bit by adding on this lambda I bit. Now, how does this actually, how does this work in the case of cubic smoothing spline? So the cubic smoothing spline is still at the top of the page here. What we want to do is I want to define an omega. So for the cubic smoothing spline, we're going to define omega to be a matrix, I'll say ij, where the ijth entry of our matrix omega is going to be the integral of two things, fi double prime at s and f double prime j at s ds, where f is our, I guess, cubic function. Cubic function at interval I, or fi, say, is our cubic function at interval I. So this matrix, okay, maybe it's a little bit opaque when I first write it down. What we're really just doing is we're doing the second derivative of a cubic. So we're basically killing off everything except for the highest order term there. And we're multiplying it by another one, and I mean the I and the jth together, and we're integrating it over all values s. So roughly, this is going to correspond to our penalty term, which is why I'm writing it down. I'll say, therefore, we had a penalty term above that looks something like the integral of m double prime s squared ds. And what we can do is we can write this as beta transpose omega beta. So, okay, again, the f's are just going to be our cubic functions, and the betas are going to be the coefficients. So when we do this integral, we're effectively just doing a quadratic form with the betas and that matrix omega. Now, again, the nitty-gritty specifics are not super critical to understand, but it's good just to have a sense of what's going on here, because I'll say, therefore, we are basically trying, right? In stats, we're always trying to minimize things. Trying to minimize, well, what? We're trying to minimize the squared error between xt, and I'm going to write f beta in the terms of the design matrix and using the norm notation so I don't have to write the sum of everything squared, because it looks a lot cleaner this way. And my penalty term is going to be rewritten in this way. So it's a lot like ridge regression, but ridge regression would be when omega is equal to the identity. Because if omega is equal to the identity, then we just have beta transpose times beta, which is just the sum of the squared betas. In this case, we're not summing the squared betas, we're modifying how the betas are summed up based on the functions f that we're applying. So in some sense, the functions f don't even have to be necessarily cubics for this to work. They just need to have two derivatives, or else I can't write down the second derivative in any meaningful way. Anyway, the result is that we have beta hat is going to be f transpose f plus, in this case, lambda, and again, not I, but omega, this omega matrix, f transpose x. So once again, we're doing the exact same thing. We have our time series. We have our smoothing operator. Well, I guess in this case, I didn't write the extra f. So, I mean, and these are the coefficients. And if I were to say tack on another f here, then I would have my smoothed process m hat t. I guess I should probably write x sub t here. Though I guess strictly speaking, I'm doing this as a vector, so no. I'm doing it for all t simultaneously, so no, I shouldn't have t there. Right, so again, it's the same idea that we're really just applying a linear transformation to the entire time series. We have x, our entire time series, and what we're doing is we're going to apply a matrix operation to it that's going to give us a smoothed out time series. And to figure out what that matrix is, we have to define basis functions, in this case, cubic polynomials. And we have to choose lambda, which is going to be our smoothing parameter. Again, our penalization parameter. If lambda is 0, we just get back to our least squares, and we're not smoothing at all. If lambda is really, really big, then we're effectively saying make sure all the second derivatives are as close to 0 as possible, and we're basically fitting a straight line. Just about all of these smoothing methods, if you take them to their extreme conclusion, you end up with just a straight line, because that's about as smooth as you can get. Right, so that's the first part of this lecture. Now what we're going to do is we're going to take a quick break while I reset everything, and then we're going to do some R examples just to show how all of this works, because I forgot to mention, I don't think I have it in my notes, that you can also do smoothing splines. I think it's spline.smooth in R. I'll double check that, and we'll apply it to that prescription drug data from the last lecture. So see you in a second. And we're back. We're going to do a little bit of RStudio now. So what we're going to do is, well, analyze that same prescription drugs pricing data set that we looked at in the last lecture, but we're going to see what happens when we apply some smoothers to it. So this was the data that we saw last time, right? And it's, again, just the cost of prescription drugs in the US from about the mid 80s to the early 90s. And I believe this data is monthly. Right, so we have this textbook data set that you can use to try out some of these methods. So again, the first thing we can try to do is we can apply, why don't we say MA, well, these are months, right? So let's do 12. Well, we can't do 12 because we need an odd number to make the moving average smoother kind of symmetric. So let's do an 11. Yeah, let's do an 11-month, or how about 7-month moving average smoother, even though it's not weeks. But in this case, what we can do is apply the filter command to the prescription data set. And what we need to do is, well, define the filter, which is just going to be 1/7 repeated 7 times. So we do that, and then we can plot lines. I think I need time prescript. I don't want lines in there. Yeah, we want lines on the outside. There we are. So we have something like this, and we can just say MA7, and we'll make it red. That is not how you spell red. All right, what is happening here? This is always the problem with doing a live demonstration. There we go. I was overthinking it. Right, so now what we have here is we have our moving average smooth process over 7 months. And maybe what I can do is I can increase the line width so we can really see what's going on there. And there, now suddenly you can really see what's happening. You see this increasing trend, and you also get the sense that there's some sort of a periodicity or a fluctuation going on with this data set. And similar to other methods, if I were to take this and say, I don't know, do something like a 23-month moving average, then it's probably going to be a lot more, even more absurdly flat. We'll make this blue and maybe change the line type just so it's easier to see. Okay, yeah, notice that we've also truncated it a bit because we're losing the beginning and the end because we don't have any window to go that far back, right? We need to have we need to slide this window across our data. The nice thing about the other methods that we're going to look at is that they don't fall into this trap. They can apply the smoothing at the boundaries of our data as well as in the center. So again, this is just your boring kind of moving average, but it is still quite a useful tool to be aware of. More interesting is the K-smooth function. So the K-smooth function is our kernel regression smoother. And yeah, you can apply it in many different ways. You can apply it to time series. You can apply it in regression context. In this case, let's see if we can. Oh, and they have a couple defaults. So for the kernel, they have, I guess, box, and then they have the normal or the Gaussian kernel. So what I'm thinking is here, perhaps they don't have other kernels implemented. Oh, better kernel smoothers are available in other package kern smooth. So yeah, there are more sophisticated ones out there, I guess, as even the function itself tells you. Maybe you want to try a more sophisticated kernel smoother, but for the sake of just explaining what's going on here, I think we'll just use this function now. because it's easy. Right, so what we can do is we can say KS will be our kernel smoothed process, and I believe it's going to want me to give it a Y or an X and a Y value. In this case, the X or the horizontal axis is just our time. And once again, I changed pre-script into pre-sip, which is a very easy mistake, which will screw up all of my analysis. So we got that. Our kernel of choice is going to be the normal or Gaussian, and the bandwidth, right? It defaults to 0.5. So again, when you first use a kernel smoother, again, this is a very exploratory tool. It doesn't really have the same feel as you would in a hypothesis test or in a structured testing setting where everything's kind of laid out very carefully before you collect the data and then go in and actually analyze the data. In this case, it's very exploratory. I have absolutely no idea what the best bandwidth is, so let's start with 0.5. It might be too small, and then what we'll do is we'll expand it. So let's see what happens. Right, let's plot our prescription data again. And there it is, and we can say lines, and this time I think I can give it a time prescript. Yeah, we'll just see what happens if I say plot KS. Every R function is always a little bit different in the way that it wants to plot. So let's see if this will do it for us. We'll make it nice and thick lines with a red color to hopefully show up on the screen. And there we go. So that looks a lot like what we saw with the seven month, I should say, moving average smoother. But at least in this case, it handles the boundaries so we can extend it all the way to the end. Yeah, we could always smooth that more or less. We could turn this to a 0.25, say, if we want to make this a little bit less smooth. And we can actually just plot that right on top in, say, blue with a different line type. And now we have in the blue dashed lines, a slightly less smooth version. If we took this to another extreme and we decided to change the bandwidth to say 2, then, well, let's do one more plot on top of this. It should look a lot like a straight line or pretty close to a straight line. And we'll do that in green. And I don't think I did that right because it doesn't look it looks more, because I didn't change this to 2, of course. There it is. So that green is actually kind of hard to see. It's actually quite interesting in this case. It looks like it's actually really overestimating at the beginning and underestimating at the end, probably because eventually it's just going to turn into a straight line. And this straight line, but it's not quite a straight line yet because I didn't over smooth it. But that's just, again, this is really just taking that normal distribution, that bell curve, and sliding it across our data and smoothing out the process. Right, so what's the next thing we can do? Well, the next thing we can do is this LOESS smoother. And that's our scatterplot smoothing, or locally weighted polynomial regression. And it gives you some references. As I said, it doesn't make it exactly clear what the algorithm is doing. Yeah, and it says the current R implementation differs from the original stopping iteration of this method. So yeah, if I had the energy, I might want to actually read the source code and see what's going on here. But regardless, it's kind of a neat method for smoothing, even if it's not straightforward exactly what it is doing to our data, which is always a little bit troublesome. Regardless, let's plug in our prescription data and see what it looks like. If I can script. Right, and in this case, we have an f, and it defaults f, our smoothing parameter, to be 2/3. So again, I don't know a priori what the best smoothing parameter is going to be, so let's just start with 2/3 and see what happens. That's the joys of exploratory data analysis. You sort of just try it and see what you get. So I think, let's see, this one should probably just allow me to plot this. And we'll change it back to red, and we'll change it back to line type 1. And now it looks almost like a straight line, right? It's not quite straight. It is slightly curved, but it looks fairly straight. So maybe we can go back to our LOESS smoother and change 2/3 to 1/3, because why not, you know? And what do we get? Well, if we change this again to blue, and we change this to, let's say, a dotted line, and I hit enter, well, it still looks pretty flat, but it is curved a little bit more. So let's try even more. Let's take this down to like 1/8 and see what happens. And we'll do this one more time, just to demonstrate the idea. We can switch this to green, even though I'm not sure how visibly visible green is in this case. Yeah, green is kind of annoying to look at, but if you can look or pause and zoom in on this, then you can kind of see that as I reduce the value of the smoothing parameter, it certainly does give me a rougher or more fluctuating smooth version of my data set. So we're getting rid of those local fluctuations, but we definitely still have some noise, some more ups and downs in there than by default, where it looked almost like a straight line. Right, and then the spline, I think, is what I want. I thought it was smooth.spline, yeah. There it is. Yeah, so for the last one, I had it backwards when I set it in the written notes. It's not spline.smooth, it's smooth.spline. And that is going to apply, well, a cubic smoothing spline, because everybody likes cubics the best, mainly because you get 2 derivatives. So it's just about enough that you can get your 2 derivatives without adding on extra derivatives that you don't really want and all that. Side note, typically you don't actually want to fit high dimensional polynomials to data, because high dimensional polynomials are really, really good at going through fitting to lots of arbitrary data points, but we don't want to model the noise. We want to model the trend in our data and not the noise. So something like a cubic is going to give you just enough derivatives to get some curvature in there without so many derivatives that you're going to start getting some crazy polynomial fluctuating up and down. Anyway, yeah, that's just the smoothing spline. So we'll say SP for spline. And once again, we're going to try and apply this to our prescription data. And you can kind of guess it's going to look a lot like all the other methods, which is how these things often go. Now we just have to figure out exactly what it's doing. And here, if we kind of work our way down, all of these have slightly different parameterizations. So it's always a little bit tricky to remember what's happening. But yeah, the smoothing parameter here is going to be lambda, but it can also, it says it's kind of an internal parameter, whereas you can use the spar argument, SPAR, which is a value, well, it says not necessarily in 0 to 1, and you can use that for smoothing purposes. So it's, again, trying to figure out exactly how to smooth these things is never quite straightforward. The joys and sorrows of exploratory data analysis. So let's just pick it at 0.5 and see what happens when we do that. And now we can once again plot our prescription data, and we can, well, let's go find my previous line. On top of that, we can plot our smooth spline, and we'll go back to red and solid line. And what do we get? We get, well, again, something that kind of fluctuates up and down a bit. So in all these cases, you're going to be getting things that look about the same. There's often not a really good reason to use one of these over the other. I mean, people have their own favorites of smoothing methods, but oftentimes you get a lot of the same results out. I mean, this does not look much different than the kernel smoother, and it doesn't look much different than the moving average smoother, but at least it gives you an idea of what's happening here. And just to take this to the extreme, if I set this, let's say if I set this to like 9.9, let's see what happens if we do that. So now if I take my smoothing parameter and I increase it a lot, then we switch this to blue, we switch this to 2, and what do we get? We get something that looks almost like a straight line, like I'm fitting a linear regression right through this data set. On the other hand, I should pick I think dark green is a color in R, so let's try that this time. If I take this and I make it a very small value, like 0.01, let's see what happens. Well, if I do that, and then let's try dark green, because I don't really like their default green. All right, now it's still kind of hard to see, but if you notice, it's actually really following the data almost exactly. So we've barely done any smoothing at all. I did want to point out that when we defined smoothing splines in the notes, cubic smoothing splines, that is, what we had was this knots. So here, you notice that in the smooth.spline method, there's actually a lot of different arguments that I was ignoring. You can determine things like the number of knots and different other aspects of this, this function. I was just using the default. So if you notice that it will just kind of default to some number of knots, knot points for your data set. But you can also specify them if you want. If you really just want a very coarse partitioning, maybe this is annual, well, it's monthly data, but maybe we would want to partition for every year, fit a separate smoothing spline for each year, at least, and then have them join up at the knots. So there's lots of different ways that you can go forward. Of course, if you actually go on to something like CRAN, the R archive network, and look, you'll find a lot of different methods of smoothing, things like smoothing in higher dimensions, lots of different tools out there. And specifically in the time series context, because again, these tools are really useful in time series, but you have to remember one thing, and that's they're really used for exploratory data analysis and not so much for things like statistical hypothesis testing. And before we end this lecture, I am going to show you an example of what I mean by that. So, okay, why don't we first, we need a new data set. So what we're going to do, not a new data set, but we're going to take our prescription data set. And if you recall from the previous lecture, we looked at the autocorrelation function. And the autocorrelation function, well, it's pretty extreme because it's not a stationary process. So what we do is we take, I'm going to call this prescript.diff, which is just going to be applying the first difference to our prescription data set. And now if I look at, let's say, the ACF of my prescript.diff, well, now I have something that's a lot more reasonable. It's telling me here that there's some seasonality, which we've already discussed in the previous lecture and which I mentioned here. But it doesn't look, we don't get that sense that it's non-stationary. And if I plot my prescript.diff, then I have something that looks like this. So that could be a nice stationary time series. Again, I don't know precisely because I didn't go back in and do the proper tests to determine stationarity. But at least if we have something like this, we could try to analyze this first difference process statistically with things like the ACF, which is what I had here. But what happens if I, say, try to smooth this out? So if I, let's say, apply a smoothing function to the first difference, we can pick whichever one we like. Let's do cubic smoothing, smooth.spline, just because I kind of like smoothing splines. I think I can still use the time command, even though I took a first difference. We'll see if R yells at me for doing that. And we'll say spar is equal to 0.5, because I kind of liked that. Oh, and I forgot to save it into I'll say PD for prescription diff dot sp for spline. Why not? Now, if I plot my prescript, if I plot the first difference, if I can hit the keys without messing that up, we have our first difference. And if I were to then overlay the cubic smoothing spline, which is going to be this thing, again in red with a nice thick line so we can see it, and that should be good, I think. Okay, so that's what it looks like when I apply the cubic smoothing spline. And once again, we really see that periodicity popping out of our data. And what I wanted to caution you about is trying to do something like looking at the autocorrelation function for a smooth spline. Because if you do, well, that is just going to get mad at me. I wonder why it doesn't like that. There's probably something to do with the time or whatever. I know, probably because it's a smoothed spline object and not a time series object. There it is. So again, we can look at the autocorrelation, and it doesn't look too different, but if we started doing some statistical testing, it might tell us something like, this doesn't really look like it's stationary maybe, or maybe there's other problems with it. And the point is that a lot of these statistical methods that we use, they're assuming there's noise in there. And if I just smooth out a lot of the noise, then we can't necessarily use the statistical methods, because it's going to think, wow, there's really no noise in this data because I smoothed it, I got rid of it. What we'll do is we'll look at an example. I don't have it ready right now, but perhaps I'll find it for the next lecture when we start doing about lagged processes, because if we try, or when we try to lag a process and then use it to predict, or regressing, I should say, one time series on another, then sometimes we can find patterns that aren't actually there if we smooth and then start trying to fit regression models to our data. So you do have to be a little bit careful, and just remember that mostly smoothing should be used for exploratory purposes to understand the data, but not for proper statistical testing. Like in this case, we can say, look at that. We see some periodicity, so I should probably try to fit a seasonal model to the data, but fit it to the original data, not to the smooth data. And that's my little soapbox rant on smoothing. But yeah, so that basically brings us to the end of this lecture. I hope that kind of gave you some interesting tools to be familiar with for when you're looking at time series or even other non-time series data yourself in the future, because smoothing methods can be a really nice exploratory tool to understand our data. And with that, we will end for today and get ready though for the next lecture, because we're going to get into proper ARIMA models for time series. And this is going to be really the big meaty part of the course. So I will see you in that lecture.